This video will begin our discussion of section 6.1. This is theory, preliminary theory for higher order linear differential equations. So a reminder of a differential equation, or a linear differential equation would have this form here, where we have our dependent variable y in this case, counting down derivatives all the way down to itself y, with a some kind of expression on the right-hand side. All the coefficients of those y's and their derivatives are functions of x or are independent variable. Now, what's going to start happening is we're going to look at what happens when we slightly change this equation. If all the numbers that are in front of my y's are constant, we call them constant coefficients. If they're not constants and they have variables, we call them variable coefficients. Here's the definition. It gets a bit tricky because we had something similar like it at the beginning of the semester, but if b of x equals 0, it's called homogeneous. Not homogeneous polar, but homogeneous. What they're saying is if this value right here, this b of x, is just a 0, then it's called homogeneous. We'll have a certain way to solve a homogeneous DE, and we'll talk about. Otherwise, if it's not a 0, it's called non-homogeneous. We also have a standard form of this type of DE, and the standard form is just to make sure that the leading derivative has the coefficient of 1. All right, we're going to talk through a BVP, which is a boundary value problem. It is exactly the same. They just give different values to solve for our BVP. So let's start here. They're going to give us a general solution. We don't even have to find it, and they want us to solve it using this general solution. So we have x of t. I'm just going to rewrite it real quick. C1 sine 4t. That way I have it all in the same color by each other. Right, and I am going to find my derivatives now. X prime, we get 4c1 cosine of 4t. And then the derivative of that cosine is going to be a negative, and then I get a 4 from the chain rule for that too. All right, so there is my derivative for x. Then I take my second derivative. I'm going to need it. The reason I know I'm going to go that far is because of here. I'm going to plug it all in here in a moment to solve for c. All right, so that, if I follow that same cosine is negative, so I get negative 16c1 sine of 4t minus 16 C2 cosine of 4t. So there we go. Okay, so what we're going to do now is we are going to work our equation to solve for c. All right, so I have x naught, or x of 0, and I know that has to be equal to 0, so I'm going to plug 0 into my equation and set it equal to 0. So we get c1 sine of 0 plus c2 cosine of 0, and I know that has to be equal to 0. Well, this is a 0, so we get c2 cosine. Cosine of 0 is 1. All right, so we get c2 is 0. All right, so that tells me that x of t then is just c1 sine of 4t. Let's keep going here. Now we can use the other value. We can take x of pi over 2, and we can plug that into x. But it's just x now is what's right above here. I don't have to do c2 anymore. So we get c1 sine of 4t, and 4, not t anymore, but pi times pi over 2. And that's going to be equal to, they told us when we plug in pi over 2, we get a 0. All right, so I worked this out. C1 sine of, okay, that gets me 2 pi. Now, this right here, sine of 2 pi, is equal to 0. So regardless of what C1 is, that's always going to work out. If I plug pi over 2 in, we'll always get it to work out because we'll get sine of 2 pi, which is a 0. So it doesn't matter what C1 is. So the solution to this BVP is a C1 sine of 4t for any C1. And let's say that's in the real numbers. This means inside of. So, or part of, an element of, I guess is a better way to say it. C1 is an element of the real numbers. It works for them all because that sine 2 pi. Right, let's take a look at this. What if we were to change our boundary just a bit? So notice there that that second initial condition now changes to when I plug in pi over 2, I get 1. So we get that same thing as before. So I'm going to write that down. X of t, let me write it down over here. X of t is C1 sine 4t. The reason I know that I can keep that is because this value, that's where I got that last time. Same thing, nothing changed there. So now, if I plug in pi over 2 equals 1, okay, so if I'm plugging this in, I get C1 sine of 4 times pi over 2 equals 1. All right, again, I know that this, all right, that whole thing there is 0. So there isn't a C. There is no such C where that works. That works. So, since that's truth, right, there's no C I can plug there and times it by 0 to get a 1, then the BVP has no solution. So the difference between IVP and BVP, I've realized I didn't really make that clear. Your BVP will give you multiple initial conditions of the same level. Like those are both position functions, right? An IVP is going to be more based on giving you just initial conditions. This is an initial condition because of the 0. This is some other value, pi over 2. It's no longer initial condition. Hopefully that makes sense to you. Initial conditions would just have all the zeros. But since it's giving me non-zero inputs in multiple, a good giveaway here is because we have two position functions. And the reason that's a giveaway is because I wouldn't plug 0 into both and get two different values, because then I wouldn't have a function. All right, we're going to change this one more time, slightly different. Notice the only thing different here is that one. So we still have x of t is equal to C1 sine of 4t. That comes from here. All right, now we need x prime. All right, x prime of t, because that's what we're going to plug in. We're going to get 4C1 sine 4t. Right, and we're going to plug in values here. So plugging in pi over 2, we get 4C1 sine, and plugging in pi over 2, we get 2 pi, and that's supposed to equal 1. Okay, well, I don't know if that's going to happen there. Sine of 0. Let's go back, and let's, instead of considering our derivative there, let's go back to our other function, because I think we can grab something out of this. So if this is my x of t, let's write down all of it. Right, and we were to plug everything in here. Let's do our derivative. Oh, I didn't even do my derivative correctly. That's why. This should have a cosine 4t, so we don't need to worry about this. We have 4 cosine, C1 cosine now, and we're not going to have a problem. We plug in pi over 2, 4C1 cosine of that, so we get a 2 pi, and now that's okay because that is equal to 1. We had a problem there when it's a sine. So we get 4C1 equals 1, which tells us that C1 is 1 over 4. Right, so the solution to this one, this BVP, is 1/4 sine 4t. Right. So they'll change. Notice that just the changing of one boundary, one condition, it's the same problem all 3 times that we did it, but changing that one boundary changed our solution. So it is important where those boundaries come from. It gives us a bunch of different types of solutions. Leading into our next types of ODEs that we're going to solve, we're going to start solving homogeneous linear ODEs. Remember, that was a linear equation except for that this g of x over here is a zero, right? It has to be a zero for this to be homogeneous. It's not homogeneous linear, it's just homogeneous. Now, a couple things I need to explain. So homogeneous linear always has a trivial solution if you let y equal 0. And that's because if y was 0, then y prime is 0, which means y double prime is 0, which means if I plugged them all in here, right, all those different derivatives, I would have 0, which of course equals 0 on the right. So it's a solution. So we always have that for a trivial solution. The reason we call it trivial is it's just 0. It's understood. If y is a solution, then I can multiply. This is superposition stuff that we kind of talked about in the last section. If y is a solution, I can multiply that solution by a constant. If I have two solutions, y and 2, then I can multiply both of those and add them together to get a solution here. Now, here's a new thing. If my solutions that are part of my solution, like y sub 1 and y sub 2, if these things are linear independent, then we gain a little bit more information, and that's where we're headed. Now, what does it mean to be linearly independent? It means that you are not a multiple of the other. That's all it's saying. There's a formal definition to it. I'm going to show you guys here in a moment. But really, the best way to think about it is you can't multiply one of your solutions by a constant multiple and get a different one. That means if you can do that, it's a linear dependent. So they depend on the others. I can pick constants to multiply by and get the other ones. If that can't find one, then they're not. I'll explain that more. So the general solution for this is you just take all your solutions, y sub 1, y sub 2, all the way through y sub n. We're talking about higher order meaning bigger than 2. We can put them together like this with all our C1s to get a new solution set. And what we call the solution set is the fundamental solution set of solutions. It's right here. As long as they are linearly independent. Now, let's explain what that looks like here. This is going to be a really simple problem. They say there's a DE. Here are two solutions. That solution, these are the fundamental solution set. It says write a general solution. So my general solution is going to be y equals C1 T2 plus C2 T to the negative 1/3. That's all they're wanting. I know it seems silly that that's all we did for that problem, but they're just trying to get across to you that I'm trying to get across to you that if I have multiple solutions that are in my fundamental solution set, I can write them like this with the C1s and C2s or C up through Cn and add them together, and it's a new solution to our DE. If we were to take the appropriate derivatives and plug it in, it would work. Now, given that with some theory, if it is the fundamental solution set, let's take a look a little more at linear independent and dependent, because if it is the fundamental solution set, we actually gain some more information. All right, so let's talk about linear independence. So if we can, and I was saying this out loud, but let's take a look at it here. If I can find a bunch of constants, C1, C2, all the way up, every single function that I'm considering, if I can find a number to put in front of them, that way when I multiply and add all that, I get a 0. If I can find those number C's, then it is linear dependent. If I can't find those numbers, then it's linearly independent. Be careful here. This gets people the way I have this written. I need to retype it. But this linearly, gosh, I can't, dependent means that works out. I feel like this is misleading. If I can't get that to work out, it's called linearly independent. So what we're looking for, here's another way to understand this. It's supposed to be a C1 here. That if I can write this, then I can solve this equation for F1. And this is what I was saying to begin with that linearly dependent. C2 divided by C1 is a constant. So if I can take one of my functions, f1 or f2, and I can multiply it by a constant and get the other one, then they are dependent on each other. Let's take an example to hopefully clear this up for you if you're not seeing it. So it says, since is x squared and 5x squared linearly independent on all real numbers. So I'm going to write out a statement. This is something that you would write on a test. You would write it this way. I get some pretty bad answers on this one for my test. So since c1 times x squared plus c2 times 5x squared equals 0, 4, and then I write out my values. Okay, c1, if I let c1 be negative 5 and c2 equal 1, then that works out, right? If I put a c1 negative 5 and a c2 1, I would get a 0. And since that works out to get me a 0, that tells me that these two functions are linearly dependent. If I can spell it. We found a C1 and a C2 that works out. So since that works out, they are a constant multiple of each other. Tells me they are linearly dependent. All right, we have 3 here. So it's the same thing. So you would sit and stare at this. What I usually do is I write it out first like it's going to be, and then I just erase it if it's not going to be. I do a lot of erasing. So since C1 times 2x plus C2 times x squared plus C3, this is times both of those, so I'm going to throw them in parentheses. 5x squared minus 4x equals 0, 4, and then I try to figure out C1, C2, and C3. All right, so I have C1 times 2x, C2 times x squared. Okay, so I see here that this x is going to add with this x right here. I would really like those to go away, so if C1 could be a 2, that would be great, because and then I would have a 4x with that negative 4x and it would go away. Now thinking about this x squared with this 5x squared, I would really like those to cancel. So maybe I can put a negative 5 for C2. And then this works out, since I didn't change either one of these, I'll just put a 1 there. So check that out. If you put in those numbers, you will get a 0. That tells me that since that is true, then the set 2x x squared 5x squared minus 4x is linearly dependent. All right, so you may be thinking now, well, what if what if the functions are much more complicated than the ones I've been choosing? What if it doesn't work out? How do you determine that you've looked for long enough? There is a much quicker, it's not quicker, there is a much more direct route to determining if they are linearly dependent or not. This is using something called the Wronskian. Right, the Wronskian is a determinant. This formula looks super intimidating the way it looks like this. We are going to do a few examples, and you're going to see that it's actually really not bad. It just looks intimidating when written out in formal language like that. So why this is important, and we're not going to get into the theory because it requires linear algebra, but if I can make this Wronskian, and this is something I can work out and get a number, if I get 0, then it is linearly dependent. If I don't get 0, then it is independent. So let's try one of these. So the Wronskian, W of t squared, and then t squared e to the negative t. And we throw this into our determinant. We put t squared, and we put t squared e to the negative t. And what this says to do, if we look at this definition, it says take your function and then take your derivatives, and we do it until we have a square matrix. Well, that means I only got to go one more, 2t. If I had to go more again, I would do 2, then 0, then 0. I would just keep taking my derivatives going down. But to make this a square matrix, since I only had 2 functions to begin with, I only need to go 1 down. Now, this is a product rule, though. 2t e to the negative t minus t squared e to the negative t. So now this is just the determinant. So we have t squared times 2t e to the negative t minus t squared e to the negative t minus 2t times t squared e to the negative t. If you don't remember this, this is like the cross product in Calc 3. We multiply those two minus multiplying those two. That is my determinant. So multiplying all this out now, we got 2t cubed e to the negative t minus t to the fourth e to the negative t minus 2t cubed e to the negative t. This equals negative t to the fourth e to the negative t. This is not a zero. So if we look back at our notes, it says if it's not zero, then they are linearly independent. So if we get a zero there, we got dependent. If we don't get a zero there, it's independent. What I like about this is it's a method. I didn't have to think about it. I had to think, I guess, to do the calculus, right? The derivatives and then do some multiplication. But I didn't have to sit and look for a couple C's. So we're going to look at some of the examples that we've already done. And I'm just going to show you how the Wronskian spits those out. So let's take a look at this next example. If we do the Wronskian of those two, x squared, 5x squared, right? I only have two, so x squared, 5x squared. And I take derivatives until my matrix is square. Okay, 2x, well, that's a 2 by 2. All right, so 10x, and then we use our diagonal trick here. X squared times 10x, we get 10x cubed minus 10x cubed, which gets us a 0. Well, that tells us that the set x squared, 5x squared, which we already knew because we found c's earlier that would work, is linearly dependent. So the Wronskian just spits it out for us much faster than the other. Now, it does get a little more heavy, a little heavier when we have 3. So this is that other example that we did. Let's try this one. So the Wronskian of 2x, x squared, 5x squared minus 4x, right? So we start filling this in, and I got 2x, x squared, and then 5x squared minus 4x, and it's 3 across, so I got to go 3 down. So derivative of 2x is 2, derivative of 2 is 0. If I had to keep going, I'd just get zeros. Derivative of x squared is 2x, derivative of 2x is 2. Then for this last one, we got 10x minus 4, and then a 10. All right, so hopefully from Calc 3 you remember this. This is a determinant. I'm going to write that word here. Try to spell it. Determinant. I think that's it. Maybe check that out. Google fix my spelling. If you need to check out some methods on there. So for this is when we do like our cross out method. We cross this out, cross that out, and we write down what's left inside a small determinant. 2x, 2, 10x minus 4, 10. And then we put the intersection here. We didn't talk about it in Calc 3. I mean, I know I don't in my class. But what we do next is we don't know the reason, meaning we put a minus here, cover up that middle one, write down what was not covered up, 2, 0, 10x minus 4, and 10. And then we put the intersection there, multiplied. Then plus, it's always minus plus, right? Then I cover those up, and I cover the third column, and I write down what's left inside there, 2, 0, 2x, 2, and then whatever the intersection there, 5x squared minus 4x is, we multiply. All right, so this is a bunch of diagonal determinants. So we get 20x minus 20x plus 8. Got to be really careful there. Times 2x minus 20 minus 0 times x squared plus 4 minus 0 times 5x squared. Those were much easier than that first one. I don't know why my brain froze up. All right, so we have those go away. So we get 16x minus 20x squared. And then we get plus 20x squared. and then minus 16x, which is 0, which tells us that this solution set 2x, x squared, or this set of functions, expressions, is dependent. So it is linearly dependent since we got a 0. So again, the Wronskian, we've already done this problem. We just didn't have to think about what a C1, C2, and C3 are. It just answers it for us. Let's take a look at one more example. And we're going to determine it's a 3 by 3, but now we have sines and cosines, so we just have to be careful. So the Wronskian of sine, cosine, 1. All right, so we put these across, sine, cosine, 1. And then we take our derivatives, cosine x, negative sine x. Cosine gets us negative sine. Derivative of negative sine is negative cosine. Then we get derivative of 1 is 0. Derivative of 0 is 0. Okay, so we cover up our first column in our first row. And we get, okay, I'm not even going to write it in there. It's 0, right? 0 minus 0. Actually, I should write it. I'll keep everything the way it should be for example's sake. And then it's times the intersection up there, so it's sine x. Then we do a minus. We move our row over. And we got cosine x, negative sine x, and then 0, 0. And then we write down the intersection up there. Move our column over. So we got plus now. Cosine x, negative sine x, negative sine x, negative cosine x times 1. We get a 0 in the first one, minus 0 in the second one, plus, and then this is where it all works out, we get a negative cosine squared, and then minus, and that's going to be a plus, so minus sine squared times 1. All right, this just gets me negative 1 times cosine squared plus sine squared, and hopefully a red flag is popping there for you. Cosine squared plus sine squared is positive 1, which leads us to a negative 1. Negative 1 is not 0. So the solution set sine x, cosine x, 1 is linearly independent since we didn't get a 0. So hopefully you understand the definition of dependent linear dependence and independence is mainly it's all about the constant multiple getting us the other solutions. The Wronskian though makes it really nice to check if something is linearly dependent or independent. The reason we're doing this is because we're going to use a method moving forward in a future lesson where this is important. We have to have this to be true before we can move on. So this was all the preliminary theory for higher order. We have BVPs. We have something called the superposition principle, and then also this Wronskian.